Swayam Prabha. Digital India. Educated India.
Now, let us go to the next idea is sum rule, product rule and Bayes theorem. The first rule is a sum rule, states that probability of x equal to summation p of x comma y if y is discrete, and integral based over y p of x comma y dy if y is continuous, where y are the states of the target space of the random variable y. This means that we sum or integrate the set of states y of the random variable y. So, the sum rule is also known as marginalization of property. Now, the sum rules relates to the distribution to a marginal distribution. In general, the joint distribution contains more than two random variable. The sum rule can be applied to any subset of the random variable, resulting in the marginal distribution of the potentially more than one random variable. Moreover, if x equal to x1 xt, we obtain the marginal function p of xi equal to integral p of x1 x2 and so on xt d of x suffix I. B, a repeated application of the sum rule, where we integrate sum out of all random variable except xi, which indicated by base I, which reads all the except I. So, this is the meaning of sum rule and associated with the discrete and continuous. So, this is also called as a marginalization property. Now, we have a note, many computational challenges of probabilistic modeling are due to application of sum rule. So, you have to make a note, when there are many variables or a discrete variable with many states, the sum rule boils down to performing a high dimensional sum or integral. So, performing high dimensional sum or integrals is generally computationally hard, in the sense that there is no known polynomial time algorithm to calculate them exactly. Now, the second rule known as the product rule, and it relates to joint distribution to the conditional distribution, that is most important. The product rule is associated with the conditional distribution. Therefore, p of x comma y equal to p of y over x into p of x. So, the product rule can be interpreted as the fact that every joint distribution of two random variable can be factorized and written as a product of two other distribution. So, the two factors are the marginal distribution. First one is a random variable p of x and conditional second random variable as p of y by x. Now, the ordering of the random variable is arbitrary in p of x comma y. Therefore, the product rules implies that p of xy equal to p of x by y into p of y. So, the equation of the conditional distribution of the product rule says that the expression is in terms of the probability mass function for a discrete random variable. For continuous random variable, the product rule expressed in terms of the probability density function. Keep it in mind this. Let us go to the next step. Now, in the machine learning and Bayesian statistics, we are often interested making inferences of unobserved latent random variable, given that we have observed other random variable. Now, we assume the prior knowledge of p of x about the unobserved random variable x and some relationship of p of y over x between x and second random variable y. So, we can observe like this, and if we observe y, we can use Bayes theorem to draw some of the conclusion about the given observed values of y. Therefore, according to the Bayes theorem, P of x over y equal to P of y over f x into P of x by P of y. So, P of x over y is called as posterior, P of y by x is a likelihood, and a priority of a probability of the event you have to get it, and total evident of the probability also you have to get it. Therefore, this is the direct consequence of the product rule of the 6.22. Therefore, probability of joint distribution P of x comma y equal to P of x by y into P of y, or P of x comma y can be written as P of y by x into P of x. So, based on that, which one is a prior to occurred of one another, and that relation bring it so that the two different category of P of xy can be get it. Now, here P of x over y into P of y and P of y over x P of x are equal if and only if P of x over y equal to P of y over x into P of x by P of y. So, these 6.24, 25, 26 are most important for what based on the Bayes theorem. So, this is the direct consequence, the product rule. Now, in 6.23 is a prior P of x, which encapsulates or subjective prior knowledge of unobserved variable x. Before observing any data, we can choose any prior that makes sense to us. So, it is critical to ensure that the prior has a non-zero PDF or PMF, probability mass function or probability density function, on all plausible x, even if they are very rare. So, for likelihood case P of y by x describe how x and y are related. In the case of discrete probability distribution, it is probability of the data y. If we were to know the latent variable x, note that the likelihood is not a distribution in x, but only in y. We call P of y by x. Either the likelihood of x is given or the probability of y given x, but never the likelihood of y, and written in the Mackay in the year of 2003, refer it, so that full description of the likelihood of P of y by x will be distributed and explained. Now, the posterior P of x by y is the quantity of interest in Bayesian statistics, because it expresses exactly what we are interested in, that is what we have know about x after having the observed y. Therefore, the quantity of P of y equal to integral P of y over x into P of x dx equal to expectation of P of y by x over x. So, this is called as marginal likelihood evidence. So, the right hand side uses the expectation operator, which we define in the section. By definition, the marginal likelihood integrates the numerator with respect to the latent x variable x. Therefore, the marginal likelihood is independent of x. It ensures that the posterior of P of x comma y is normalized. So, the marginal likelihood can also be interpreted as the expected likelihood, where we take the expectation with respect to the prior P of x. So, beyond the normalization of the posterior, the marginal likelihood also plays an important role in the Bayesian model section. So, we will discuss in this due to the integration of the evidence often hard to compute. So, Bayes theorem allows to invert the relationship between x and y given by the likelihood. Therefore, Bayes theorem is sometimes called a probability stick inverse, and we will discuss the Bayes for further section of Bayesian statistics. The posterior distribution is the quantity of interest as it encapsulates all available information from the prior and the data. So, instead of carrying the posterior around, it is possible to focus on some statistics of the posterior, such as maximum of the posterior. So, we will discuss in the section. However, the focusing on some statistics, the posteriors leads to loss of information, and if you think in a bigger context, the posterior can be used within the decision making system, and having a full posteriorly can be extremely useful and lead to decisions that are robust to disturbances. For example, in the context of the model based reinforcement learning, in this book Dyson wrote et al. In the 2015 shows that using the full posterior distribution of plausible transition function leads to very fast learning. So, whereas focusing on the maximum of the posterior leads to the consistent failures. Therefore, having the full posterior can be very useful for downstream task. So, this chapter we will continue the discussion in the context of the linear regression. Now, we have a summary of statistics and independence. So, let us start with the definition of means and covariances. For the definition expected value, the expected value is a map from R to R of G. So, the G from R to R of the univariate continuous random variable x is approaches to P of x is given by expectation of g of x over x equal to integral over x g of x into P of x dx. Correspondingly, the expected value of the function g of the discrete random variable x maps to probability of x given by E of g of x over x equal to summation x in capital X g of x in P of x, where x is the set of all possible outcomes and random variable capital X. So, these are all the conditions you take it, corresponding expected value can be determined from domain to codomain, then it is called as univariate continuous random variable. Now, we have a note. Consider a multivariate random variable x as a finite vector random variable. For the multivariate random variable, we define E x of g of x equal to E x of g of x1 and so on E x of g of x, where belongs to Rd, where the subscript exd indicates that the expected value with respect to dth element of the vector x. So, keep it in mind, the expectation related to n d elements are given, then corresponding expectation we can write in terms of the matrix. And next we have a mean. Take the mean random variable x that states that x in Rd. So, the average and is defined by Ex of x is equal to Exn of x1 and so on Exd of xt in Rd, where Exd of xt equal to integral over x xt into P of xt dxt if x is a continuous random variable, and summation xi in x and xi of P of xt equal to x, where x is a discrete random variable. So, there are the two cases which arise the expectation for d equal to 1 to d, where the subscript d indicates the corresponding dimension of x, and the integral and sum over x states that the target of the random variable x. So, in one dimensional there are two other intuitive notation of average mean, where the median and the mode. The median is the middle value if the sort value, that is 50% of the value are greater than the median and 50% are smaller than the median. So, this idea can be generalized to continuous values by considering the value where the CDF continuous distribution function is 0.5. So, for the distribution which are asymmetric or have the long tails, so the median provides an estimation of typical values that is closer to human intuition than the mean value. Further, the median is more robust to outer lines than the mean. So, the generalization of the median to higher dimension is non-trivial, as there is no obvious ways to sort in more than one dimension. So, the mode is most mission of using the three orders Halil, Kong and Mizera. So, the mode is the most frequently occurring value. For discrete random variable, the mode is defined as the value of x having the highest frequency of occurrence. For a continuous random variable, the mode is defined as a peak in the density of P of x. So, a particular density P of x may have more than one mode, and furthermore there may be a very large number of modes in high dimensional distribution. Therefore, finding all modes of the distribution can be computationally challenging. Now, based on that, we will go to the example. Consider two-dimensional distribution illustrated in the figure 6.4. This is the 6.4 figure, right? Mean, mode, median, and then P of x equal to 0.4 of n of x over 10, 2, and comma the matrix 1 0 0 1, and plus 0.6 n of x over 0 0 comma 8.4 2 2 1.7. So, we have to discuss in terms of the Gaussian distribution of n of mu comma sigma square, also shown in the corresponding marginal distribution in the each dimension. Observe that the distribution is a bimodal as a two modes, but one of the marginal distribution is unimodal and it has a one mode. So, the horizontal bimodal univariate distribution illustrate that we mean, median can be different from each other, while it is tempting to define the two-dimensional median to the concatenation of the median in each dimension. So, the fact that we cannot define an ordering of two-dimensional points make it difficult. So, we say cannot define an ordering, we mean that there is a more than one way to define a relation less than, so that 0, 3, 0 is less than 2, 3. So, this is the explanation of what we just described, the Gaussian distribution, where rose color represent the mean and star denotes the mode, and a square bracket of red color define median. So, based on this, the Gaussian distribution is discussed, and keep it in mind where the ideas of bimodal is explained. So, this is the two-dimensional distribution and keep it in mind. So, let us go to the next ideas. Now, we have to make a note that the expected value is a linear operator. For example, the given real valued function f of x, which is equal to a into g of x plus b into h of x, where a comma b in R and x in Rd. So, we obtain that expectation of f of x over x equal to integral f of x into p of x dx. You take f of x equal to a into g of x plus b into h of x, substitute it. So, it becomes a into g of x plus b into h of x into p of x dx. Since it is a linear and product them, so they are splitted into two integral. So, here a is a constant, take it outside. Therefore, integral g of x into p of x dx will come, plus b into integral h of x into p of x dx will come. So, this is the meaning of expectation of g of x, this is the meaning of expectation of h of x, and then e of x, f of x is what? Linear function. So, it is a linear operator. So, we can split it into two functions like that. So, next definition, the covariance univariate. So, the covariance between the two univariate random variable x comma y in R is given by expected product of their deviation from their respective means, that is covariance of x comma y of x comma y is equal to expectation of x comma y into x minus ex of x into y minus ey of y. So, that is the meaning of covariance of both x comma y. So, one in terms of x y of the product of two random variable of x and y. So, this is called as two univariate random variable. Now, we have a note, when the random variable associated with expectation or covariance, therefore, by argument the subscript is often suppressed. An example, ex of x is often written as e of x. So, by using the linearity of the expectation, The expression is a definition and rewritten as the expected value of the product minus product of the expected values. Therefore, the covariance of x comma y equal to E of xy minus E of x into E of y. So, that is the easily can represent the covariance in terms of the expected value, and it will be very useful for finding the covariance is a linear expectation or not, and the covariance variable of the coefficient of covariance of x comma s is called as a variance and denoted by Vx of x, and the square root of the variance is called as a standard deviation and it is often denoted by sigma of x. So, the covariance can be generalized in the multivariate random variable. So, all the formula we have to remember, then we can incorporate it with the real time problem. Next definition is a covariance of multivariate. If consider two multivariate random variable x and y, which states x in Rd and y in Re, then respectively the covariance x and y is defined as covariance of x comma y equal to expectation of x comma y transpose minus expectation of x into expectation of y the whole transpose, which is equal to covariance of y comma x transpose in R d cross E. Now, by definition can be applied with the same multivariate random variable in both arguments, which results in usual concept that intuitively capture the spread of a random variable. For a multivariate random variable, the variance describe the relationship between the individual dimension of the random variable. So, the definition is a variance. So, the variance of a random variable x with states x in Rd and mu in Rd is defined as variance of x equal to covariance of x comma x. So, already we demonstrated the covariance of x comma x is expectation of x minus mu into x minus mu whole transpose. Further, we can get into expansion of Exx of x transpose and Ex of x into x transpose. Now, we can write in terms of the matrix. So, we have a D cross D matrix covariance of 1 1, 1 2, 1 D and 2 1, 2 2, 2 D and so on, D1, D2 and so on Dn. So, variance of x can be written in terms of the matrices of the covariance. So, covariance of x is denoted by 6.38c formula. Now, we have a picture corresponding to the example of the definition. So, D cross D matrix in 6.83 is called the covariance matrix of the multivariate random variable x. So, the covariance matrix is a symmetric and a positive semi-definite, and we have data spreading the data on its diagonal. So, the covariance matrix contains a variance of the marginals like this. So, if x and y are negatively correlated, the picture comes like this. If x and y are positively correlated, then the picture is like this. So, there are the two dimensional data sets which are identical, both means and variance, but they have different covariances. And see, that is a symmetry of this, and one is based on left and another is right. So, the based on negatively represent in terms of the left and positively represent the right, and the scattered how they in left they same scattered in the right in the positive, and this is two dimensional data sets of identical mean and variances. So, like that we can bring the ideas about the symmetry, right. Symmetry in the sense that x axis and y axis you take it and then transpose to one another, they are equal in the normal matrix, and see the picture, they have a same type of the picturization in the left direction, right direction. and this way we can write the applications. And based on this we have a cross covariance, that is p of xi equal to integral p of x1, x2 and xt of dxi, where slash I denotes the variable, all variables, but I the off diagonal entries are the covariance terms of the covariance of xi comma xg. So, in this talk we generally assume the covariance matrices are positive definite to enable better intuition. So, we therefore do not discuss the corner cases of the result in the positive semi-definite of the covariance. Next definition, correlation. So, the correlation between the two random variable x and y is a CORR of x comma y is a covariance of x comma y by root of variance of x into root of variance of y. So, this is lies between -1 to 1. So, the correlation matrix is the covariance matrix of the standard random variable of x over sigma of x. In other words, each random variable is divided by standard deviation. So, the square root of the variance in the correlation matrix. Now, we saw the figure, right, this 6.5, and then the covariance and correlation indicates how two random variables are related, and they are positive correlation of the COR of xy means that when x grows, y is also expected to grow, and negative correlation means that x increases and y decreases. Next, empirical means and covariances. So, the definition in this section are often called the population mean and covariances. So, it refers the true statistics for the population. In machine learning, we need to learn from empirical observation of the data. Consider random variable x. There are two conceptual steps to go from the population statistics to the realization of empirical statistics. First, we use the fact that we have a finite data set, that is of a size n, to construct the empirical statistics, that is a function of a finite number of identical random variables x1 to xn. Second, we observe the data, then we look at the realization of x2 xn of the each random variables and apply the empirical statistics. Specifically for the mean, given a particular data set, we can obtain an estimate of the mean, which is called empirical mean or simple sample mean. The same holds for the empirical covariance. For the definition of empirical mean and covariance, the empirical mean vector is the arithmetic average observation for each variable and is defined by x bar equal to 1 by n into summation n equal to 1 to n xn, where xn in r power d. So, similarly, the empirical mean, the covariance of d cross d is denoted by summation is 1 by n summation n equal to 1 to n xn minus x bar to xn minus x bar transpose. So, this computes the statistics for a particular data set, and we have the realization observation x1 to xn of the equation 41 and 42. So, the empirical covariance matrix are symmetric, positive, semi-definite. So, these are all the important things you have to know. Next, three expression for the variance. So, we need to take care of the integrals. The standard definition of the variance corresponding to the definition of covariance is the expectation of squared deviation of a random variable x. So, from the expected value of mu, so the definition is V of x over x is expectation of x minus mu the whole square. So, this expectation of 43 equation and the mean mu equal to expectation of x over x are computed using the 32 equation depending on whether x is a discrete or continuous random variable. So, the variance of the expression in the equation 43 is the mean of the new random variable z equal to x minus mu the whole square. So, if you estimating the variance in the equation 43 is empirically, we need to resort to the two pass algorithm. One pass through the data to calculate the mean mu and the second part pass to the estimation of mu bar, calculate the variance. It turns out that we can avoid two passes by rearranging the terms. The formula 6.43 can be converted to the so called row score formula of the variance. So, V of x over x is equal to expectation of x over x square into expectation of x the whole square. So, this formula you have to remember for variance of in terms of the expectation. So, the expression of the 44 can be remembered as the mean of the square minus the square of the mean. So, literally you can keep it in mind, the mean of the square minus square of the mean is called it as what? The expectation of the variance of the x. So, it can be calculated empirically in one pass through the data, since we can accumulate xi. So, we have to calculate mean and xi square simultaneously calculate. Xi is the ith observation. Unfortunately, the implemented in this way can be numerically unstable. So, the raw score version of the variance can be useful in the machine learning. For example, when derivation of the bias variance decomposition is using, refer the book Bishop 2006. So, the third way to understand the variance is, it is the sum of the pairwise difference between all pairs of observation. Consider a sample x1 to xn and a realization of the random variable x, and we compute the squared difference between the pairs of xi and xj. By expanding the square, we can show that the sum of the n square pairwise difference is empirical variance of the observation. Therefore, 1 by n square summation I comma j equal to 1 to n xi minus xj the whole square equal to 2 times of 1 by n to summation I equal to 1 to n xi square minus of 1 by n to summation I equal to 1 to n xi the whole square. So, this also we can write the empirical variance in terms of the formula of the sample space x1 to xn. So, the pairwise if you are given, then you have to do like this. So, the sum of the pairwise difference between all the observation can be calculated using the equation 45. So, we see that the equation 45 is twice the row scores expression of the equation 44. This means that we can express the sum of the pairwise distance of some deviation from the mean. Geometrically, this means that there is an equivalence between the pairwise distances and distances from the center of the set of the points. So, a computational perspective, this means by computing the mean and computing the variance, so we obtain the expression the left hand side, that is n square terms. So, this is the meaning of variance and this. Thank you.